Okay, so in this first section, we'll quickly go over some background information about electric power system, and we'll focus on the introduction of the electric power generation, and also share something about the planning, the designing, and operations of today's power systems. This figure gave you the trend of the utilization of the energy resources for electricity in the past 73 years, because this is describing from 1950 to 2023. So for almost half century, actually longer than half century, the coal has been the major resource of generating electricity. So until maybe 2005, and the utilization of coal for generating electricity reached the peak. And then you see, this is basically talking about the U.S., not the other countries. So then the U.S. started retiring the coal-fired power plant, and meanwhile it just increased the natural gas power plant. So later when we talk about the detailed principles, so we know why this is was decision made at that time. So this red color indicates nuclear. Nuclear starting become flat. It doesn't change too much if you compare the size to maybe 20 years ago. They basically stay about same. But I don't know, maybe in the next few years, there may be slight increase in nuclear. The main reason is because of the quickly increase the load from a data center. The data center has been a very huge, large load, and they need to have very reliable electricity supply. But usually they are located in some area far from populations, so you have to build new transmission infrastructure, so that can impact the existing power grid and change the distribution of the load, the customer. So some large company like Microsoft or Google, they're considering, or maybe they're already moved forward to build a new nuclear power plant. It can be conventional nuclear power plant or macro scale power plant, so to provide more reliable supply of electricity to their data center, because AI training or AI load will become very quickly increasing load. The green is renewable. But in this figure, the green include all type of renewable, including the hydroelectric power, wind, solar, and other type of renewable. Okay, so if we show the pie chart, so today, let's see if we talk about 2023, maybe 2 years ago, the natural gas will be the #1 resources for electricity generation in the country. #2 will be nuclear, then will be the coal. Okay, renewable hydro take 6%, and the other renewable, including wind, solar, and also there are other new type of renewable, they take about 17%. So that's today's generation of electricity. If we map those colors into the map of the U.S., so color may be slightly different because we have to use the green to indicate green and yellow to indicate two different type of renewable resources. Like green indicate wind, and yellow indicate solar. The coal is still a dark gray or black. Natural gas is brown, and nuclear is dark red, and hydroelectric is just blue. You can get an idea on where those resources are, how the electricity is generated in different areas. So for example, we'll stay in Tennessee, right? And Knoxville is probably here. You can find a nuclear. There's a couple of large nuclear power plant. And also the dark color is coal. We also have a coal-fired power plant. And also a lot of blue dots indicating we have the hydroelectric power plants along the Tennessee River and its branches. For the entire southern area, you see a lot of small dots of yellow, which means the solar power is largely utilized in the southern area. That's also the same case of the southwest area. You see California, Arizona, they have a lot of solar power. Large dots of blue, which is hydropower, is mainly on like the border of to Canada, and anywhere you see large river, right? That will be hydroelectric. And what is interesting is if you find wind is mainly in this area, in the Midwest. Okay, so because there's a very rich resource of wind. The next map we're going to see is where customers are. This is from the outer space. So for the other type of resources, they match that map very well, but the wind is very different, right? Wind stay in the Midwest area, but in the Midwest area, there are not many people there. So if you want to use wind to generate electricity, you have to figure out a way to deliver electricity to either to the west or to the east. You have to build a long transmission. And this is today's transmission network. So in the eastern side, the power network is very dense. The highest voltage can be 500 kV. There are a lot of high voltage transmission. It's a very dense grid. And for the western area, because it's a Nevada state and a lot of desert there, so the transmission network is like a ring surrounding Nevada. So, and in the Midwest, there's not many high voltage transmission. Okay, so it will be interesting to compare those three maps together to get an idea on where electricity generated, where electricity utilized, and how the electricity delivered. I hope by the end of this this class, you will have a big picture about what today's power system is and what challenging problem we're going to face. Next, let's show some the curves about the loads, and then we talk about the generation. So assume this is the load curve for 24 hours for one city area. I show two curves, one is for summer, the other for winter. So what can we guess by looking at those two curves? Do we know where this city is? Yeah, it has to be some cooler area because the winter load is higher than summer, right? So it cannot be Arizona. Otherwise, the summer will have higher AC load. So this is very likely to be a cooler area. But if we only talk about one curve, this is a very typical load curve we can have, because if you take a look at the one peak hours will be around 12 o'clock, right? That's most of people are already awake, and they will stay for the daytime until maybe 8 p.m. The curve will go down, and around 4 o'clock, most people are actually sleeping, so the load is minimal. So we have the peak hours from maybe 2 to 4, and we have the minimal load around 4 o'clock. So summer is about similar case, right? Sorry, winter is about similar case. All right. So another thing we can find from the load curve is definitely they only represent two typical days, one in summer, one winter. But if you can find the load curves of all days, all 365 days, you can find there may be some load which will be there all the time. Like for example, this 6 gigawatt load. Any load curve will be above 6 gigawatt load. So what that means, this one will be the basic load, or base load. Base load means the load is there maybe for almost 100% of time. So we call it a base load. If I have one type of generation, the generation is not very flexible to be turned off or turned on, but it is very cheap. So I need to use that type of generation for baseload. I just only need to keep that generation on all the time, right? We can maybe the maintenance operation cost can be high, but if I keep it on, so that will be a very economical solution for such system. But also there may be some other type of load. They just appear at a large percentage, but not 100%. So this figure, X is from 0 to 100%, and Y is about the same load level of the system. So you see for 100%, the 6 gigawatt load will appear for 100% of the time, which means 100% chances you will have load at 6 or under, 6 gigawatt or under. But above 6 gigawatt, the percentage will decrease from 100%. For example, for the whole year, you have 9 gigawatt load. That chance is only maybe 70%. And above 12 gigawatt, that chance is only around 1%. So we can categorize the loads of the entire system into 3 types: the base load, the intermediate load, and peak load. The base load means they will be on all the time, and intermediate load will be on for 70% of chances. Then peak load only appear at very rare times. Then we can study how we can utilize existing energy resources to power those loads. So we have a hydroelectric power, we have a natural gas power plant, we have a coal-fired power plant, nuclear power plant, solar, and wind. So to power the base load, usually the nuclear power should be utilized to support base load, because to turn off and on the nuclear power plant can be very tricky, very hard. I need a long enough time, maybe a couple of days. For any coal-fired power plant, it also need maybe 10 hours, 5 to 10 hours to start this coal-fired power plant. So once it is running, you want to keep it run forever. Okay, so those tools will be utilized to support the base load. So if you are a designer or planning engineer for one power system, you need to first count how many nuclear power plant, coal-fired power plant you have, and those will together support your base load. And based on the load curve, you'll know, okay, my system has 6 gigawatt base load. My nuclear power plant and coal-fired together can take maybe 5 gigawatt. So there's still 1 gigawatt I can utilize natural gas. Okay, so together they will give you this base load. And for the intermediate load, that needs some energy resources they can easily turn off and off, because they still appears at very high chance, but not 100% time. So natural gas power plant can take a few minutes to start. So if I can predict how the load will increase, maybe for example, so here, so when the load is climbing up beyond 6, so I will quickly plan which natural gas to start and to pick up this load, and also I can use a hydroelectric power plant. For the peak load, which appear around 1% of chance, I can only utilize some power plant which can react very fast. Natural gas can still be utilized, and another is like pump storage, hydroelectric, they can be utilized to power the peak load. So this is basically how we dispatch existing power plants to power the load of the entire system. But we haven't talked about the renewable, those 2 types of renewable, solar and wind. So there will be a question mark on where the solar or wind go, right? Either go to the base load or intermediate or peak. Where? Any idea? So what is the largest difference for those 2 types of new renewable energy resources compared to those conventional resources?
They're not constant.
Yeah, they're not constant. All those, okay. Yeah, So rigorously speaking, this is pretty constant, right? That's based on the nuclear fuel you have. So you know how much you can control the output, and this is same, and natural gas same. Hydroelectric, there are two types. One is the pump storage. That one you can really control how much electricity generated. There are another type of run out of river, so that has less control, but mainly those conventional resources are pretty constant compared to renewable. Maybe a better terminology is not constant, it's like those two are more intermittent. Intermittent means if I predict the wind will be strong for 2 hours, the power output can be constant, but for some other day, the wind may not be that strong, so I will lose that energy. So now the idea of using those two renewables is to use them as much as possible. Okay, so if you have because those are like free energy. If you don't use those energy, you lose the energy. All right, so I draw another load curve. So this load curve, I call it the demand faced by conventional power plant. So what that means is if you have a lot of solar and wind integrated into the system, and the load curve faced by conventional power plant will be like this curve. Yeah, let's see why it become in this way. Because, as I said, we try to utilize as much renewable as possible, considering them as a free energy. The solar will be more from sunrise to sunset. The peak time will be in the early afternoon. So you can treat this area will be the electricity generated by solar. Okay, because we have that much of solar energy, so we fully utilize that energy. That will reduce the load curve to become this one. And the other two will be changed by wind, because wind usually is very strong in the early morning around 4 o'clock. So this part of energy or power will be supported by wind, and also there's a late night. Okay, so that seems to be a good thing because you have a less load supported by conventional power plant. So those power plant, the operations or their fuels really cost money, but those are free, right? The resources from sunlight and from wind, they're free. So the total energy integrated under this curve is much smaller because this energy is taken by solar. Those two energies are taken by wind. But what changes, the base load is also changed. The base load is not 6 anymore. From this figure, it can become 4, right? I have to draw a new line here. So base load is changed. So if for system is the entire base load is actually supported by nuclear or coal-fired power plant. But because this curve is changed, I have to more frequently turn on and off maybe some coal-fired power plant. So that can introduce some risk of reliability. How many of you have heard of this term, dark curve? A dark curve, yeah, good. Dark curve especially talk about what's happening in California when they have more solar photovoltaic panels installed in California. The curve describes exactly what their utilities are facing, because this still describe the load curve for the entire day. But you see the shape is very different from what we see from the previous slides without renewable, right? Remembering in the past, there will be peak load here, right? Starting from 10 o'clock to early afternoon. Let me draw here. A typical load curve should be like this one. But this entire area is actually taken by solar power. So about 10 years ago, the people realized in the next 5 to 10 years, so the load, so they say like 2015. That's exactly, it's already happened, different from a conventional load curve. But they predict in the next 5 to 10 years, so this point will become deeper and deeper. Finally, it will become negative. Negative means at this time, the California, the load become negative because the load can completely supported by the solar power at that moment. And solar power is even more, which means if California is connected to neighboring state, neighboring power system, they are actually exporting electricity to other states. And why they call this curve as dark curve? Because it's really like the shape of dark, like dark. So it becomes deeper and deeper. So this is like 2022. So it can introduce huge reliability risk because if you check this slope, it's very deep. So what happened at this point is, so here, the California ISO area is exporting electricity to neighboring state. Assume the neighbor can take that electricity. If they cannot, they have to turn off maybe some of the generation because they cannot allow the generation to be higher than load. But at this time, and then suddenly at 5 o'clock, and it will quickly, the load will quickly go up. Because why? Because that's around the close to the sunset time, and the solar radiation is largely decreased. So they have to have conventional generation to pick up the load when the solar decline. So this slope can be as high as 10 gigawatt in 3 hours. So that is already higher than most of the conventional power plants. So the fastest speed to ramp up the generation. So they have a lot of challenge. So they either have to keep those conventional generation running all the time. They keep certain, like a natural gas power plant running all the time, but they are not generating any electricity, it's just running a motor. And when they at this time, they just quickly generate electricity from those units. So although you can consider renewable as free energy, but the conventional generation, they also need to run. They cannot just be turned off. Otherwise, they cannot just increase as fast as this line. Another solution is they have to build a lot of battery energy storage. The energy storage through power electronics, they can quickly support the load if they have enough energy saved in the battery. So from this example, we know renewable energy is not free. Although the wind and the sunlight are free, but to generate electricity from solar and wind energy is not really free because the integration may introduce some additional reliability cost. All right, so okay, let's talk about the first conventional generation resources. We talk about the hydroelectric power plant. This is the Norris Dam hydroelectric plant located in about 25 miles the north of the Knoxville. So if you drive on 75 to the north, you will see this this Norris Dam plant that now is become state park. So that's the first hydro plant built by TVA back to mid 1930s. So it has operated for almost 100 years, 90 years. So the principle of generating electricity from the hydro power plant is you have the water here, right, at a certain elevation. So assume this height is h, and the water will carry potential energy. So when you let the water flow through this channel, which is called a penstock, it will have some speed and will become kinetic energy. Will turn the turbine and the generator and then generate electricity. So that's the principle is very simple. So if you go inside of the power plant, you will see a lot of generator. And the generator is placed, the axle is vertical. very different from other type of generator. So later when we go to the generator modeling session, we talk about this generator will be the ceiling pole rotor generator. And for the steam turbine, the gas turbine, so the generator will be a round rotor generator. So such generator have large, very large diameter, so they'll operate at a lower speed. To calculate the electric power generated by a hydropower plant, so we can use some parameter about the power plant to do a very good estimation. So assume the overall efficiency is eta, which can be very high. And this height is h, and the rate of flow is q. And we also know the water density, which is about 1,000 kg per meter cube. And also we know the gravity. So we can quickly calculate. The power output will be the efficiency multiplied by the power carried by the water. Okay, and the power from the water will be the kinetic energy divided by time, right? And kinetic energy also is potential energy. So to calculate potential energy, basically we assume there's some water at this height and a certain volume, and multiplied by density and gravity. So that will be the weight of the water. So when it flows through this channel, will become the Q. So that will be the formula to calculate the power output of this power plant. Okay, let me just stop here. So we'll continue on Wednesday. Oops.